Section 20.3, Mineral Properties. So we classify minerals by their chemical composition, so what they're made up of, and how they're structured, their crystal form, their crystal structure. So if you know those things, then you know what mineral you have. It's the easiest way to figure out what kind of mineral you have. This is because things that you see when you look at a mineral depend on microscopic and submicroscopic properties. So how it looks depends on the way that it's structured at a submicroscopic level, the way that it's put together and what it's made up of. So if you know those things, then you understand how it looks. However, sometimes the way that it looks can be different from what you would see if you broke it down. So the structure and the composition and the strength of the bonds are what determines a mineral's crystal form, and that's really what determines the mineral itself. When you have that particular crystal form of a mineral, it has other properties associated with it. Things like hardness, which is a resistance to scratching, how easily it can scratch something else, or how easily it can be scratched. You also have fracture or cleavage, which refers to how a mineral breaks, whether it just shatters into pieces or whether it breaks upon particular planes. And then you have some other physical characteristics like color, what color it appears to be, and then the density of that particular mineral. Now, most minerals you can identify with these properties. If you know the crystal form and composition, you pretty much know the mineral. But you can use the other properties as well. A few others that you'll notice that we'll talk about are what's known as luster, which is the way that a mineral reflects light, and streak, which is what happens when you have a mineral in powdered form. So even the most common minerals can have some really fancy shapes when you look at them under a microscope, when you look at how these atoms are all arranged together in these particular minerals. And a mineral's crystal form is an expression of the arrangements of its atoms. The way that it appears under a microscope is an expression of the way the atoms combine together to form the mineral itself. Each mineral has a unique composition and a unique structure. It's made out of something and it's structured a particular way. That's what determines what kind of mineral it is. However, there are some minerals that we call polymorphs that have the same atoms, they're just in different arrangements, different structures. And because the structure is different, they're different minerals, even if they are the same atoms. The same elements make them up. One great example is graphite and diamond. They're both carbon. They're just made out of carbon. They're just made out of carbon in different arrangements. Graphite is what you write with in your pencil, and diamond is what we put in wedding rings. Diamonds have this particular lattice structure here. It's very hard to break a piece off of one of these atoms. They're all connected to each other. It'd be very hard to just break a chunk of this off. But graphite is connected as just sheets of carbon atoms. These are the exact same type of atoms. They're just structured in a different way. Because of the way that they're structured, you get two different minerals. Same atom, same structure means the same mineral. Same atom, different structure could be different minerals. So when we talk about the hardness of a mineral, we talk about its resistance to scratching, not how easily it breaks. And so the ability or the lack of ability of a mineral to scratch another mineral is a measure of its hardness. You can take two rocks and try to scratch them. If you take one rock and try to scratch it and it doesn't do anything, take the other rock, scratch the first one, because it should scratch the first one. What that means is the second rock is then harder than the first rock. Harder materials can scratch less hard materials. So when we talk about hardness, we use what's called the Mohs scale. And the Mohs scale just gives you particular elements or particular minerals and their associated hardnesses on a scale of essentially 1 to 10. The hardness itself depends on the strength of the bonds within the mineral. Again, diamond has that particular structure where it's really hard to break off any of those carbon atoms. And because of that, diamond is one of the hardest materials known to man. There's very little that can scratch diamond. So you tend to have stronger bonds when you have atoms that are small and more tightly packed, like carbon atoms in a diamond, or when you have a strong electric force between those atoms, holding them together. And so we can look at the Mohs scale, and this is just an example of a few. You have talc, gypsum, calcite, and notice things that we know in particular. Objects like your fingernail have a hardness of about 2.5. a copper wire or a coin has a hardness of about 3.5. You can use these objects to test the hardness of particular rocks. And as you go up, some other minerals, feldspar, quartz, topaz, and then at the top, you notice diamond. Diamond's one of the hardest minerals there is. Now, in terms of cleavage and fracture, this is referring to how the mineral itself breaks apart. Minerals can only break along planes of weakness or in weak spots of their chemical bonds. So you saw in the image of graphite a few minutes ago those flat planes. There we can have those planes break apart very easily. If you have a giant chunk of graphite, you'd be able to break it apart along one of those planes relatively easily. So when we talk about cleavage, we talk about the tendency for it to break along a particular plane of weakness like that. And some minerals are just structured in sheets or some format where they can break at that particular plane of weakness. You have weaker bonds on those planes than you do in the rest of the mineral itself. And that makes it more likely to break along those planes. If there's no planar alignment, then those minerals will always fracture. They'll always break apart, and they just break apart into pieces, not into flat planes or along a particular flat plane. So this can tell you something about what the mineral is made out of. If it has a plane of weakness it can break along, then that tells you something of the structure. If it can only fracture, that tells you something of the structure. Another obvious property is color. And though it is something very obvious that we see every time, it is not very helpful in distinguishing what particular mineral you have, or identifying minerals. This is because you can have small chemical impurities in particular minerals that will in turn generate very different colors. For example, if you've ever seen quartz at like the geode store or whatever it is, quartz is still silicon dioxide, essentially, SiO2, and it comes in all sorts of different colors. Corundum, which is aluminum oxide, that's the same mineral that makes up rubies and sapphires. And those two things are very different colors. And it comes from chemical impurities inside of those particular minerals that give it that particular color. If you then take those minerals and essentially powderize them, so there are things called streak plates where you can drag a mineral across the plate, and you get what is a powdered form of the mineral. Any streak left behind by the mineral is going to look the same regardless of the color. So those two streaks will have the same color. So if you were to take a ruby and a sapphire and scrape it across a streak plate, you would get a streak that looks the same. It's just the mineral in a powderized form. You can use color and streak to identify minerals that have a metallic or a semi-metallic luster, which means they're kind of shiny or kind of shiny. The final property we're going to talk about is density. Density is just a property of matter. It is just a ratio of an object's mass to its volume, how much stuff in how much space. Another way of thinking about density is just how heavy something it is for its size. Right? You have a ping pong ball and a golf ball. They're about the same size, but the golf ball is heavier. The golf ball is heavier because it is more dense. As we were talking about earlier, iron's more dense than things like silicon and oxygen, so that's why that iron sank down to the center of the earth. This is what allowed for gold miners in the 1800s to pan for gold. If you sift through dirt and water, heavier elements like gold will fall to the bottom. And so over here you can just see a table that shows the density of just some various minerals. Gold and silver being relatively dense, things like borax and quartz being relatively not so dense.